In this podcast, we're going to talk about electron configuration. Okay, so let me set the stage here. So we talked about Bohr's model, which is where you have energy levels, which are essentially rings that the electrons travel in circular orbit around the nucleus. We already know that Bohr was only right for hydrogen, but I wanted to show you the evidence that led us there and also tell you how Bohr was correct. So, first off, this is the element sulfur. Okay, so you see down here, here's sulfur, right? So it's telling us it's sulfur. And sulfur, in a sulfur atom, we know that we have, so sulfur has 16 protons and 16 electrons when it's neutral. So we would have predicted, based on Bohr's model, that we would have had 2 electrons in the first shell, 8 in the second shell, and then 6 in the third shell. So that's kind of what we would have predicted for the Bohr model. But we do know that Bohr's model failed to be able to calculate emission spectra for the elements. All right, so this down here is showing us, so on our y-axis over here, this is number of electrons, okay, and it's telling us the energy required to remove the electrons. So I do want to point out that we have 2 electrons here. If we add these 2 peaks together, we have 8 total. And then if we add these other 2 peaks together, we have a total of 6. So Bohr was not wrong about energy levels per se, but notice how there is further division in the 8 and the 6th ring, the second and the third ring. So this means that there's further organization going on for the electrons than just being in rings. So while they aren't necessarily in rings, they're further organized than that. We do know that they are the same kind of distance from the nucleus. So like we know that these 2 are very close, these 8 are a little further out, and then these 6 are very far out, okay? So still supporting some of Bohr's theory. Okay, so that kind of leads us to this idea of an orbital. So an orbital is a probability map of where an electron can be found in an atom. So basically, if we go there, there's a 95% chance that we're going to find an electron. A guy named Schrödinger described 4 orbitals, known as S, P, D, and F. Now, all of these orbitals, and they're also called sublevels, have different shapes. Okay, so we're still going to talk about energy levels, rings, right? So we've still got rings going on. Okay, now within each ring, we have different amounts of orbitals. Okay, so S orbital is the only thing in the first ring. In the second ring, we have a S and a P orbital. Third ring, we have a SP and D orbital. And then fourth ring, SP, D, and F. And then everything beyond the fourth ring, SP, D, and F. At least that's all we know as of right now. Now, also understand that each of these SPDF orbitals, there is potentially more than one of them per sublevel. So, for example, there's actually 3 p orbitals for every sublevel. So when I'm saying p, there's actually 3 of those. Each orbital is going to hold 2 electrons. So if you'll notice, S is going to hold 2 electrons total. P is going to hold 3 times 2, so 6 electrons total. The D orbital is going to hold 10 electrons total, and then the F is going to hold 14. Okay, so now if you kind of back it on up here, hopefully you'll see how this all connects. So let me do a little erasing right here. Okay. All right, so if we go back up here, notice that, so for S, you get 2, right? So on the first ring, we still have just 2 electrons. Okay, second ring, we have an s orbital and a p orbital. It's a total of 8. So that's consistent with what Bohr said. Okay, and then if you keep going and doing this, you'll see that it's always consistent with what Bohr said. They're just further organized within the energy levels into these little orbitals. Okay, so let's look at the shape of the orbitals and talk about their energies. All right, so s orbital is the simplest. It's very low energy. It's the first orbital that an electron is going to pop into, and it is shaped like a sphere. It holds 2 electrons. All right, the p orbital, there are 3 of them. You can kind of think of them as existing on the x, y, and z axis, which is basically like you've got one that's going up and down, you got one that's going side to side, and then the z-axis is kind of like going into the board, coming out of the board kind of idea. Combined, they look like that, kind of crazy. They are higher energy level than S, and we know that each of the orbitals holds 2 electrons, so that means all of the P's can hold 6 electrons per energy level. Okay, so here's just another little image of them all going together. So there's your X, Y, and Z p orbitals. All right, next is the d orbitals. There are 5 d orbitals. Each is going to hold 2 electrons, so that's going to be 10 electrons total. These are much higher energy than S's and P's. And as you notice, they just start getting crazier looking as you go up. And then you see like this one doesn't even match the rest of them, right? There's this whole anti-bonding molecular orbital theory that describes that, but that's a little beyond what we're at right now. And so I kind of just describe these as looking like a 4-leaf clover. All right, now the f orbital is super high energy. It can hold a total of 14 electrons, and as you see, it's very, very crazy looking too. About the best way I can describe it as is kind of thinking of it as kind of like a double clover or something, because some of them have 8 lobes, but it's definitely much more complex. Okay, so here's like a summary picture that puts all the orbitals together. So you got the S's, the P's, the D's, and the F's. And remember that you're going to have an S on every energy level. You're going to have a P on every energy level, starting with the second one and out, right? So second, third, fourth, fifth, sixth, etc. And then the d orbitals, those are going to start on the 3rd energy level, or the 3rd ring, and then F start on the 4th. All right, so here's like a nice little summary chart. So we've got our shapes here. So S is sphere. P is described as traditionally as looking like a dumbbell. I kind of think the p orbitals look like an infinity sign personally, or like an hourglass maybe. D, I described that one as kind of looking like a 4-leaf clover, and then F is kind of like a double clover. We know that there is 1 S, 3 P's, 5 D's, and 7 F's per energy level. Each of those holds 2 electrons, so that means total, the S holds 2, the P holds 6, the D holds 10, and the F holds 14. The first energy levels we see them are S is on the first energy level and everything after that. P shows up on the second one and everything after that. D comes in on the 3rd one and everything after that. And then F is on the 4th ring and everything after that. Okay, so now let's compare this to that periodic table that we've heard. Okay, so we talked about the S, P, and D and F orbitals, right? Okay, so first off, I want to point out that notice that the S's start at 1 because they are on the 1st energy level and everything after that. And if you count the boxes in each row, you will notice that there are 2 boxes in each row that are S's, and that is consistent with the fact that the S can only hold 2 electrons, and there's only one S orbital per energy level. All right, P's are over here. We know that the P's can hold a total of 6 electrons, and if you count your boxes going across here, it is 6. We also start the P's at the second energy level. All right, D orbital is right there in the middle. If you remember, there can be 10 total electrons. So if you count going across here, it is 10. And it first starts on the third energy level, and that's what the first D orbital is called. It's 3D. And then we have the F's down here on the bottom, all the radioactive synthetic guys. And they hold 14 electrons. If you count across there, there's 14 boxes, and F starts on the fourth energy level. So hopefully that'll help you remember. It matches up completely with the periodic table. Okay, so this kind of leads us to what we're trying to do here. So we want to be able to describe where all of the electrons in a particular atom are, down to the energy level and then down to the sublevel, okay, which means the orbital. So I want to know how many do I have in that orbital in that energy level. So these big numbers in front, these represent the energy level, or the ring, the distance from the nucleus. All right, the letters S, P, D, or F, those are our orbitals or our sublevels. And then the little exponent looking things, these are our electrons. Okay, so let's talk about sodium. So sodium's electrons, so sodium has a total of 11 electrons, and we want to describe where each of those electrons are. So to do that, we are going to first get out our handy dandy electron sequence periodic table. We're going to note where sodium is on the periodic table. All right, so sodium lives right there. Okay, and we know he has 11 total electrons. All we need to do is write the electron configuration, which is basically the description of where all his electrons are located. To do this, always start up here at the top at 1s. And what you're going to do is you're going to write the energy level in the orbital and then count the boxes going across the periodic table to determine how many electrons are in that orbital. So, for example, on this first one, I got 1s, and then I got another one. So I'm going to write 1s, and then I counted 2 total boxes. Okay, then just like a book, you would go down to the next line. So I'm going to go down here to my my 2s line. Okay, and so I'm going to write my 2s, and then I'm going to count my boxes. 1, 2. So I've got 1s2, 2s2 so far. Okay, and then keep reading across just like a book. So I would go here. Got 2p. Count your boxes. You should have 6 boxes. And then, like a book, continue, go to the next line. We end up on the 3s. And you want to stop where your element is. And our element is right there. So that is the first box. So 3s1. Okay, so sodium's electron configuration is 1s2, 2s2, 2p6, 3s1. So that's telling us exactly where all his electrons are located. Okay, now from this, you can draw Bohr diagrams. It is necessary to do the electron configuration in order to draw a Bohr diagram for everything that has more than 20 electrons, because they don't always fill the way Bohr kind of thought they would. So this is our energy level. So first energy level, that'd be the first ring. And then here's my electrons. So I got 2 electrons there. All right, second energy level. So I got 1 here and 1 here. So that's a total of 2 plus 6. So 8 electrons. And then third energy level, only got 1 of those, and there is 1 electron. So that's how you could draw the Bohr diagram off of that. But what the heck does that all mean? All right, so this is going to be our XYZ coordinate plane. Z just gives us the ability to try to think about this in three-dimensional space, because that's the way real life is three-dimensional. All right, so we're gonna call this little blue dot here in the center, we're gonna call that the nucleus. And so first thing that happens is the electrons go into the 1s orbital. So we have 2 electrons that go into the 1s orbital. 1s orbital shaped like a sphere, so there you go. All right, next, after the 2 electrons have filled it up, they're going to go to the 2s orbital. 2s orbital is, again, a sphere, but it's a larger sphere because it's going to be further from the nucleus. Once you have filled up the 2s orbital, you're going to go to the 2p orbital. Okay, now remember there's 3 of them, so I'm going to have my p orbitals go here, and eventually you get all 3 of them in there. So each of these little lobes is basically got an electron in it, and there's 2 electrons in this little yellow s orbital, and then underneath that was the 1s orbital that also had 2 electrons. Okay, so far we've gotten through 1s2, 2s2, 2p6. And then the very last electron is going to go into the 3s orbital. We only have 1 electron, so the 3s will not get filled up. Again, it's a circle, so it's just going to be, you know, a larger circle because it's further from the nucleus. All right, so here's kind of a sliced out image of what's going on. So what we've just done is we've described exactly the location and the orbital position of every single electron in a sodium atom. Okay, now I will never ever ask you to draw something like this. I just want you to conceptually understand what it means when we write electron configurations. Okay, so let's do a few more examples for electron configurations so you feel a little bit more comfortable. All right, so let's find the electron configuration for aluminum. So first thing you want to do is you want to mark where aluminum is on your periodic table so that you can trace it through. We do know that aluminum has 13 electrons, so there is aluminum. All right, remember, always start at 1s and count your boxes. So 1s, and there's 1, 2 of those, so 1s2. And then you go to the next line, so there's my 2s, and I count my boxes, 1, 2, so 2s2. And then reading across like a book, I got 2p. Okay, and count on my boxes, going through 2p, and you see we got 6 boxes. Keep going to the next line, so that gets me to 3s, and there's 2 boxes in the 3s. And then last but not least, keep reading across, we get to the 3p, and aluminum is located in the first box. So all that's going to do is finish it out with 3p1. Okay, I don't like how that all got bunched together there, so I'm going to erase these right here so it doesn't look like that. Okay, so there's my electron configuration for aluminum. Aluminum has 13 electrons, so at the end of the day, if you did this correctly, all of these exponents should add up to 13. All right, and last one, let's look at the electron configuration for iron. So first, let's mark where iron is on the periodic table. Okay, so that's where iron is. So again, start up here at the top. So I've got 1s2, 2s2, 2p6, 3s2, 3p6. Now this is where it gets a little interesting, because after 3p, go down to the next line, that is actually the 4s, okay? So you actually fill the 4s, so you go up to the s orbital on the 4th ring and fill it before you start filling the d orbital on the 3rd ring. That's all about stability, and because the d orbital has very high energy, so it's it's harder to get your electrons to occupy that orbital. Okay, so starting with our 3D, now we're going to count over. So 1, 2, 3, 4, 5, and 6. Okay, so there's our electron configuration for iron. Now, as an added little bonus, I'm also going to do the Bohr diagram because I think it's important you understand the correlation. So remember the numbers in front tell us our rings. So first ring, I got 2 electrons. That comes from my exponents. Second ring, there's 2 of those. So on the second ring, I've got 2 plus 6, so 8. All right, and then third ring, this is where it's a little tricky because I've got 3S, 3P, and then here's 3D over here, so you can't forget that. So you actually have 8 plus 6, so 14 on the third ring. And then on the fourth ring, you have 2. Okay, so this is where electron configuration helps us with visualizing correctly Bohr diagrams.